All right. Good morning, everyone. Can you all hear me? Yeah, okay. I think this is working. Great. Awesome. So, as we said before, we're going to start talking about a couple of other cross-coupling reactions that fall under the bigger umbrella of transitional metal catalyzed reactions. And the first one that we're going to address today is the Stille coupling. So, Stille coupling. And it distinguishes itself from the Suzuki reaction that we have been talking about during last class in that it actually uses stannanes, so tin compounds, instead of the boronic acids. So the transmetalliting agent is something like, let's call this R and SN R prime. So it's usually a tetraalkyl stannane, and the residue that is going to be transmetallated is usually this residue R here. We're going to talk about these here in just a little bit. But if you think about an example, the Stille reaction works more or less the same way that you would have expected after learning about the Suzuki reaction. So in this case, let's say we have again a triflate here, and we react this with a stannane. In this case, we can pick like a vinyl stannane, for example, SN, and then it has like these three other substituents on here. And let's call these here, because most of the time they're butyl substituents. Let's call this tributyl stannane here. And then the reaction conditions for these are very similar. So we need a palladium catalyst. We can use palladium tetrakis here again. We can use a solvent like THF for these reactions. And usually, in order to make this work better, there is a variety of additives that can be thrown into the reaction mixture. Most often, this is just simply a salt like lithium chloride or something like that that accelerates the reaction. And out of the reaction comes, as expected, the coupling product that you see here. And in this case, we can basically just add this vinyl group to the aromatic rings, so we have stilbene essentially here, or styrene in this case specifically. Now, what are the advantages of using this Stille coupling? So there are certainly some clear advantages over Suzuki reaction. So advantage. And the first one is that it does not often does not require strong bases as part of the reaction mixture. So if you have functional groups that are unstable under basic conditions or could be hydrolyzed under basic conditions, Stille coupling gets around that. So does not require strong bases. Then the other advantage to the system is that this stannane reagent here that you see over here is much easier to purify than the boronic acids. And that's simply the case because we can run standard columns on these systems where boronic acids, for example, would be stuck to our immobile phase. So the purification of these stannanes is a lot easier. So stannanes are easier to purify than boronic acids. And lastly, oftentimes the Stille coupling gives you more reliable and better yields. Tends to give higher yields. Now, the obvious question here is now, why the hell do we even use Suzuki reactions if all these advantages essentially point towards Stiller reaction being like the system of choice? Well, the problem is that it comes with one major disadvantage. So all these positives here come at a significant price. So the disadvantage is that all of these stananes here, all these tin reagents, organotin reagents, are terribly toxic. So in a laboratory setting, just for the simple acute toxicity of these compounds, we usually avoid them and take the hit in the yield or take the more difficult purification pathway here, just because the safety of the lab personnel is a much higher priority. So stananes are usually used in the lab as really the very last resort if all the other coupling reactions have failed or have not given any workable yield, right? So it's not definitely for the toxicity, it's definitely not our first choice. So the tin compounds are often very toxic. And it turns out that the toxicity correlates very much with the size of these additional 3 alkyl groups here. So the butyl substituted ones, the N-butyl substituted ones are not that bad. The trimethyl substituted stananes are really toxic. And it does not just apply to the reaction, but you have these as a waste product in your waste stream too, and you would have to collect them separately and dispose of them separately. So it brings in a lot of additional hassle that you avoid by using the other more traditional Suzuki coupling reactions. But it's a viable alternative if you run out of options, then you can switch to Stille coupling. Now, the point that I want to make here about these stannane reagents is that you see that you have 3 alkyl substituents that are identical here, and then you have the group, the R group, that you actually want to transfer, right? And there is a trend, potentially all of these can be transmetallated, but there is a trend that favors some of these alkyl groups here, especially the unsaturated ones, to transmetallate long before these simple saturated alkyl groups transmetallate. And we're going to talk about this a little bit. So transmetallation. Trends. So the relative order of transmetallation, so if we just look at like our classical SNR3, and I think we called this prime, and then we have our R here that we actually want to transmetallate. So the trend here is that the sp hybridized carbon atoms attached to the stannane are much easier to transmetallate than the sp2, and then of course than the sp3. So that leads to a trend that, for example, alkynes attached to our stannane, R3 prime, are much faster transmetallated than, for example, vinyl substituents, SN R3 prime. And those are more or less the same as aryl substituents. So if I have an aromatic ring here, SN R3 prime, and those are a lot better than just a simple alkyl. So how do we write this? Alkyl SN R3. So the trend is clearly that the alkynyl are substituted much faster than the vinyl, and these are more or less the same as the aryl. And the last one that gets substituted is the simple alkyl. There is a couple of people who are not muted in the system. Can you please mute yourself? Because otherwise I hear constant background chatter in my headphones. Yeah. Let's see it all. Okay. All right. So that means essentially that if we have a standard reagent buildup like this, where R this R prime here is a simple alkyl substituent, we can make sure that anything that is an alkynyl, a vinyl, or an aryl is transmetallating faster than any of these three other substituents on here. Now, this also puts a limitation on the Stille coupling, because if you just want to transmetallate an sp3 hybridized carbon atom, this is significantly more difficult because you don't have the selectivity with all four different substituents on the standing. So Stille coupling useful for sp and sp2 hybridized alkyl or aryl groups. And less useful for sp3 hybridized alkyl. Now, the last thing that we want to quickly talk about is like how to make these stannanes, and that's relatively straightforward. And we can use a similar trick as we have used previously for making the boronic acids. So we can start from a simple Grignard reagent, so something like this, for example, magnesium bromide here. Or, for example, you could use also an alkyl lithium reagent that's more or less the same. It works exactly the same. And then you treat this with a stannane precursor, and usually these are some trialkyl stannol chlorides. So something like this. And then let's say a commercial one is, for example, this tri-N-butyl stannol chloride. And that basically just does like a simple transmetallation. You generate magnesium, the mixed magnesium salt or lithium chloride as a side product, and you get your stannulated reagents. So SN butyl 3. So this is basically your stannane, something like this up here. And then in this case, you get magnesium chloride. Or in this case, if you use the organolithium reagent, you get lithium chloride, right? And well, these can be basically used as they are generated in this reaction, and they're easy to purify and to separate. All right, so this is as much as we want to talk about the Stille coupling. If you were to draw the reaction mechanism, it works exactly the same as with the Suzuki reaction, so there's no point in repeating this. The only thing that you have to switch out is essentially the transmetallating agent from the boronic acid to the stannane. So if you want to practice this at home, this would be a good idea to kind of practice a little bit the cyclic mechanism of these transition metal catalyzed reactions. Now, from the Stille coupling, we want to move on to another class of cross-coupling reactions. And again, they are characterized by a different transmetallating agent, and these are called the Kumada coupling. And so Suzuki coupling was with boronic acids. Stille coupling was with stannanes. The Kumada coupling is exactly the same mechanism, just now that the transmetallating agent is a Grignard reagent. So transmetallation. From Grignard. So in this case, then, if we were to draw out an exemplary reaction, we could use, let's say, let's use like something a little bit more exotic. Let's use a pyridine. And we have in the 2 position installed a bromide. And now we treat this with our transmethylating agent. In this case, this is the Grignard reagent. So magnesium bromide. And then the reaction conditions, again, are very similar. We can use our standard palladium tetrakis. And we use THF. The important thing in this case is that you have to make absolutely sure that these conditions are dry, because remember, Grignard reagents react as bases. So if you have like any water around, this Grignard reagent will be quenched under these conditions, right? And the product of this then is simply the cross-coupling product of the pyridine with the aromatic ring here. Now, what is the clear advantage of this? Well, think about it this way. Grignard reagents, we have used them so far as the precursors to make, for example, boronic acids or to make the stannanes. So you would cut out one step in the reaction of making your cross-coupling reagents by directly using the Grignard reagent in this transmetallation. So Kumada couplings are usually synthetically a little bit shorter because you only have to prepare the Grignard reagent and use it directly rather than turning this into the stannane or the boronic acid first. Now, the downside of this is that, as I mentioned already, these Grignard reagents are strong bases and strong nucleophiles. So that limits you a little bit in what functional groups you can have present in your substrate in order to perform this reaction. If you have anything in your substrate, for example, that could be deprotonated, so an acidic proton, or a functional group that is an electrophile, like a carbonyl or an aldehyde or something like that, that could react with a Grignard reagent, these reactions are not compatible, right? So you can then have to switch over to use the Suzuki coupling or the Stille coupling. So just as kind of a downside or disadvantage, let's say Grignard are strong bases and strong nucleophiles. And it's essentially incompatible with carbonyls or acidic functional groups. Because it will preferably then react as a base or as a nucleophile. And essentially, this is one of the key reasons why from Kumada coupling, the Suzuki coupling and the Stille coupling have been further developed in order to avoid basically this, this basic effect and this nucleophilicity and the very limited substrate scope that you could use these Kumada couplings for. All right, so all of these reactions so far, so Suzuki coupling, Stille coupling, and Kumada coupling, all of them worked based on exactly the same cyclic catalytic cycle that we discussed as part of the Suzuki reaction. So again, the only thing that you would have to switch out in this cycle is what specifically your transmethylating agent is going to be, whether it's going to be a boronic acid, whether it's going to be a stannane, or whether it's going to be a Grignard reagent in these reactions, right? The next type of cross-coupling reactions that we want to look at a little bit closer are a little bit more involved because they use additional steps in the catalytic cycle that we have not seen so far. And the first one that we want to look at is actually the Sonogashira coupling. So Sonogashira. And Sonogashira is a very specific cross-coupling reaction that only applies to sp hybridized carbon atoms. So it's essentially a cross-coupling of an alkyne. Cross-coupling of alkyne. The other exotic thing that comes with it is that it actually uses two metals. Two transition metals in the reaction. The first one is, again, palladium. So that's the classical catalytical role that we have seen before. So we can use palladium tetrakis, for example, in this reaction. But the other metal that is key is that it uses copper as a catalyst within these reactions. So you can think about this as a very generic example of the Sonogashira reaction. You can have a terminal alkyne. So let's say something like this. And it's important that it's terminal. So it needs to have this hydrogen here on one side of the triple bond. And then you can mix this with, let's say, our cross-coupling partner in this case could be an aryl halide, for example. Let's say we use the aryl bromide, and this can have many substituents here. So I'm just going to abbreviate this here with R prime. And then the catalytic conditions, again, are a palladium 0 catalyst. So let's use our standard palladium tetrakis again. You need copper, and usually this is copper 1, so in the first oxidation state that you use here. So in this case, we can use copper iodide as a common one, or copper bromide. And then you need an amine base, and this is usually some secondary amine, so diethyl amine, or a tertiary amine like triethylamine. All of these work quite well in these reactions. And now the product of this is essentially the cross-coupling of this terminal alkyne. So this sp hybridized carbon atom here is attached to the position on the ring where the bromine was previously. So you're going to get something like this, right? So direct coupling of this carbon atom, which was this one here, to the position on the aromatic ring where you previously had the bromide, right? That's a very, very useful transformation because this alkyne gives access to a ton of chemistry that you could do in this position. So you can do addition across this triple bond. You can do the reduction to form a simple alkyl chain. If you use a poison catalyst like Lindlar's catalyst, you can turn this into an olefin, right? So there's a lot of variety of functional groups that you could introduce with this approach. Now, the catalytic cycle is a little bit more involved, and you might have expected this because we have two different metals participating in that, and that's what we want to talk about next right now. In order to do this, I probably have to turn the page this way. I'm going to move it up a little bit so you can see it stepwise, right? But again, we would be starting out from a palladium 0 species. So in this case, for example, we can have in our catalytic cycle palladium, and I'm calling this Ln. And this, of course, is in equilibrium with the precursor, which would be something like palladium Ln plus 2 or something like that. So this could be our palladium tetrakis that loses two ligands to go down here, so minus 2L and plus 2L on this side. And now we've accessed the catalytic cycle where we now have an open coordination site for our substrate. Now, the first step in this reaction, in the Sonogashira reaction, is exactly the same one as we had discussed for the Suzuki reaction, and that's the oxidative addition of our aryl or alkyl halide. So we can draw the first arrow this way, to get to our first substrate. And here we can bring in our aryl halide. And let's just keep this very generic here, and let's just basically say this is an X here, right? And this is basically our oxidative addition again. Ox addition, right? So whereas we had the oxidation state 0 here on the palladium, now after the oxidative addition, we have palladium Ln, and then we have here our aromatic ring. And on this other side, we have the X, and this is now essentially the oxidation state +2. So it's identical to what we have seen before. Now, the next step would be the transmetallation, right? That's kind of like classically in the reactions that we have seen so far, where either the boronic acid, the stannane, or the Grignard reagent would come in and transmetallate and exchange essentially the substituent X here. Now, if you remember, in the reaction, we originally did not have actually a transmetalliting agent. We just had the terminal alkyne and this copper. And these are basically the components that come into play here in the second cycle that we're going to draw down here. So it starts out with something, let's call this copper X. So this is basically in other halides. There's copper chloride, copper bromide, or copper iodide. And this is in the oxidation state, 1 here. And this copper reacts with an alkyne, with a terminal alkyne, and we can draw this in here. So let's say RH, something like this. And what the first thing that this copper does is that it forms something that we call a pi complex with the triple bond. So you're going to have something that looks a little bit like R triple bond, and then H. And then you have the copper coordinated to this through the pi system. So you can draw this out as kind of like a bond like this. Now, if you think about this a little bit closer, so this is a pi complex. If you think about this a little bit closer, and what this essentially means for a bond between the copper, you can think about this just as an overlap between the d orbitals on the metal. So let's say we have a metal here, and we can draw in one pair of the d orbitals, and they look a little bit like this. I'm going to draw the shading here. And then you have the pi bond over here. And you can quickly see that you can form a favorable overlap between these orbitals here and these orbitals here, which would be basically an overlap between the filled d orbitals and the empty pi orbitals. So this would be pi star. And this is just a filled d orbital on the metal. So this is kind of like the type of interaction that you create in this pi complex here. It's a coordination of the copper to this pi system. Now the effect that it has is what we are actually after, because it increases, it lowers the pKa of this hydrogen, or increases the acidity. So it lowers the pKa of terminal.
Oh, Professor, can you move the sheet of paper up a little bit? Thank you.
Okay, can you see it now? Okay, great. So it lowers the pKa of the terminal hydrogen, and that's essentially what we are after. That's why we needed the copper in the first place here. Now, at the next stage, you take advantage of this lower pKa by abstracting now this proton, or deprotonating this. And that's where you essentially need the base in this reaction. So you can draw an arrow here. And what did we use? Diethylamine, I think, in the last one. So let's say R2NH. And what we kick out here is then the protonated form R2NH2 plus. So it's a deprotonation of this proton. And what we're left with then is an end coordinated copper. So it switches basically from this pi coordination side to the position where this hydrogen was, and you end up with something that looks like this, right? And this is actually now your transmetallating agent. And if you look closely, it looks very much like the stannane that we have seen previously. Just in this case, instead of a tin, you have a copper here. And if you compare it directly to the Suzuki reactions, for example, it's the same thing. You have an alkyl group attached to a metal. In the Suzuki reaction, it was a boron. In this case, now it is a copper, right? And this is the transmetallating agent that takes part in this reaction. And as it passes through this process, it regenerates essentially your copper, your original copper starting material here, right? So this step here is now transmetallation. And obviously what we expect to see here then is that we have the exchange of this X with this residue R here. So the next species would be then Ln palladium. We will still have our arrow ring here. And we have now down here our terminal alkyne. This is still +2 oxidation state. You can pull this down a little bit so that you can see the top again. Okay, and from this state, it's very obvious how we get back to our original catalyst. We just do a reductive elimination that's essentially exactly the same step as we have seen before in the Suzuki reaction. So from here, we go back to our starting material and we kick out the product in the form of the alkyne now attached to the aromatic ring. That's 3 and R over here. So this is again our reductive elimination, right? So if you have a closer look at this mechanism, this top part here is essentially identical to all the other cross-coupling reactions that we have seen before, that we've discussed before. The only new thing is essentially the in situ generation of your transmetallating agent from this terminal alkyne. And that's where essentially the second metal comes in. This copper makes this pi complex, and then this pi complex increases the acidity of this proton here. This proton gets abstracted by the base, so it just snatches away. This is a simple acid-base reaction. And the copper takes on this position here. That's actually next here, sorry. Takes on this position here and then moves back into the catalytic cycle, right? Okay, so that's as far as we want to take the Sonogashira reaction. The key to that is that it is only effective for the terminal alkyne. So you can apply this reaction only to substrates that are of this nature here. So where you have a terminal alkyne that you want to couple to a vinyl halide or an aryl halide, right? Okay. So the last reaction that we want to talk about today is the Heck reaction. And this is like the most complicated mechanism that we are going to be talking about as part of these cross-coupling reactions, because it involves a couple more steps that you haven't seen before. But it builds on the same mechanistic principle. So the Heck reaction. So the interesting thing with the Heck reaction is that you do not have a transmetallating species present here. So this thing works without actually having to use a transmetallating agent. So no transmetallation. In the mechanism. But the substrates that they use are quite familiar to what you've seen before. So again, you use some form of an aryl halide. Just going to keep this generic again with an R here. And then the substrate for most of these are double bonds or olefins, vinyl groups, right? So something like, let's say, you have something like this here. Let's call this R. Let's call this R prime here, and this is R. And all you need in order for this to work is a palladium catalyst. So again, let's use our standard palladium tetrakis here, and you need a base for this reaction to work, to soak up the acid that you're going to be producing as part of this. The product of this is going to be the coupling of this aryl halide to this vinyl group. And the interesting thing is that we don't have to do a transmetallation here to make this work. It basically just falls in place like this. So you can imagine that essentially one of these protons here at this position, without being activated to form a transmetallating species, just kind of adds into this aromatic ring here. Now, the interesting thing is, how does the reaction do this without requiring a transmetallation? And again, the catalytic cycle is a little bit bigger, so I'm just going to move this up a little bit. We can pull this down when we need it. And I'm going to use this paper upright. Okay, so the catalytic cycle for the Heck reaction, again, starts with some palladium 0 precursor. So I'm going to avoid this equilibrium, this pre-equilibrium right now from palladium tetrakis to palladium diphenyl phosphine. So I'm just going to write here Ln palladium. This is an oxidation state 0. And I just assume that this already has an open coordination site to react with the substrate. Now, the first step happens to be exactly the same as we have had before, the oxidative addition. So that's kind of like our starting point again. And we can bring in our substrate here. In this case, it was just kind of a simple aryl halide or something like that, right? Now, what comes out of this, we know already. It's Ln palladium, and since this is an oxidative addition, this is now plus 2. And then we have an aromatic ring attached here, and down here we have our halide. So this is basically the same thing as we had previously. This is an oxidative addition step as we had in all of the other catalytic cycles too. Now, the difference comes at this stage where we traditionally would have a transmetallation, but since in our reaction scheme, we don't have any additional metal, we just have this olefin here, right? There's no additional metal that could act as the transmetallating species. So we have to find a way to kind of get this olefin on there onto the complex without changing anything too much with any other transmetallating agent. So the way this works is that you essentially have a simple ligand exchange reaction where one of these ligands here is displaced by the olefin. So let's see if we can draw this down here. So let's do it like this. So we replace one of the ligands Ln here by this olefin. So let's say HR, and we kick out one of these ligands L. And the species that you get out from that looks a little bit like this. You have palladium, then you have one ligand L here. You have your X remaining on here. You have your aromatic ring on this side. And then down here, again, very similar as we had drawn it previously for the alkyne, the copper coordinating to the alkyne, you have the palladium coordinating to this double bond of the olefin, right? So this is again a pi bond between the palladium and the p orbitals on of this pi bond. So we can call this again pi complex. Pi complex. All right. Now here comes the key step that is very unusual for all the transition metal catalyzed reactions that we have talked so far, and this is called a migratory insertion. So you can think about this as essentially very similar. Just as a thought experiment, think about this the same way that you would do a double bond R, and you add, for example, HBr across that double bond, right? So what you get is an insertion, a migratory insertion, at least that's what it's called when it's a metal, where you basically have then R here, you have bromine here, and hydrogen here. Right? So you basically added HBr across this double bond. And you can think about this exactly the same way, just at this time from this pi complex, you add this palladium carbon bond here across this double bond, right? And we call this the migratory insertion. So here's the pen. Migratory insertion. So it's the addition of this palladium carbon bond across this double bond. So you get something out that looks a little bit like, can you see this down here? I'll move it up a little bit. Let's say palladium, and then you have the aryl group. And then you have the hydrogens here. And you have the residue R. And you have a hydrogen here. And then you still have, attached to the palladium, you still have an X. And you still have a ligand L here, right? So this is nothing else but an addition of this palladium carbon bond across this double bond. And you see that it's cis selective. So the palladium and the aryl ring attack from the same side onto the double bond. So you can say like cis selective addition. So they're on the same side. Okay, now in order for this process to go one step further, we have to do a little bit of a change in the system, and the key we need to do is we need to rotate around this single bond. So it's basically just a little rotation around this this carbon-carbon single bond that places then a hydrogen in this position right next to the palladium. So you can think about this as rotating by just 120 degrees, right? So let's draw this like this. So there's an equilibrium here, of course, where now we can redraw this species. So palladium, and this time we rotated. Which direction did we rotate? Okay, so then this is R, this is hydrogen. To the back, we have our phenyl ring, and to the front here, we have that hydrogen, and then we have an L, and we have an X over here. Okay, can you see that? Okay, so all we did is basically we rotated around this bond in order to place this phenyl ring into the back, and now have basically a hydrogen next to this palladium. So these are basically now in the same plane. And the key to this to the next step is that this hydrogen comes very close to this palladium, and basically this palladium abstracts this hydrogen, and we call this a beta hydride elimination. So that's the other mechanism that is new in this catalytic cycle, and that is called beta hydride elimination. And what this essentially does, it abstracts this hydrogen and regenerates a double bond between these two that is then coordinated to this palladium, to the remaining palladium, the same way that it's coordinated over here. So the species that we're making here then is, how do we draw this? Let's say, phenyl, and we have R over here, and then we have a coordinative bond to the palladium, and this palladium still has the ligand L and the X attached to that, and on the other side it now has this hydrogen here that came from this position here. So I'm just going to encircle this here. This is basically this hydrogen here that we shifted over. So from here, then it's pretty straightforward to get back to our starting material, because this is basically just the same structural species, very, very similar structural species as we had over here. And we can simply do a ligand exchange again, where this L that we kicked out here replaces this olefin again and gives us back our product. So we can draw an arrow like this here, where an L comes in and kicks out our phenyl. This is basically the coupling product that we were interested in. So let's draw an arrow here. And then the palladium species that remains here is then going to be palladium L, and then we have an X remaining here, and we have this hydrogen. So this is the hydrogen that essentially came from this position here. And this basically regenerates our catalyst by kicking out HX as the acid side product. So this basically is kicked out, and you generate HX. If this is an halide, this is basically just an acid that you're generating, and which is quenched then by the base that you had in the reaction mechanism. So overall, it might look at a first glance as a little bit more complex, but if you take a closer look, it still follows basically the main dogma of these transition metal catalyzed reactions. You have an oxidative addition here that leads to the first species with the palladium and the halide attached. So the palladium inserts essentially in the alkyl carbon X bond here. Then the new step is this ligand exchange, where one of these ligands is displaced by the olefin, and you get to this pi complex here. And then this is kind of like the new chemistry, where you get a migratory insertion. And just a reminder again, this is nothing else but essentially the palladium version of an addition of HBr across a single double bond, right? You're very familiar with this reaction from last semester, right? Now you have this addition species, and in order to get now the palladium catalyst out again, you have to rotate around this bond to place the hydrogen across from this palladium. Then you do a beta hydride elimination, which is basically just a reverse step of this. You don't, instead of kicking out the phenyl again, which would give you back this one here, you basically abstract the hydrogen. And then from here on, it's basically a ligand exchange again, and back to your original catalyst. Now, one thing that is key as part of this to note here is that this rotation around this bond necessitates that the product of the Heck reaction is going to have a trans relationship of these two substituents, because you have to place the phenyl ring here, the hydrogen in a position that is next to this palladium. This residue comes to lie on the opposite side of this phenyl group. Now, you could have rotated it to the front too, but then there would be steric hindrance between these two. That's unfavorable. So you rotate it to the back, and that gives you basically this, this E conformer of the double bond. So this is E selective. Right? So even though we started out with something here that had the hydrogen and the R on the same side, the product is always going to be the E-selective product in this reaction. All right, so last comments to the Heck reaction, and this relates a little bit to this critical new step of the migratory insertion. Note migratory insertion. Now, you of course have two possible ways how you can do the migratory insertion. So let's say you have an olefin that looks like this, and you react this with this palladium species. I'm just going to abbreviate this here, palladium LNX, something like this. Then you potentially have two ways to insert into this. So the palladium could either go in this position here, or it could go into this position. So there's two different positions that the palladium could end up with, right? So with an arbitrary R, you can expect to get two migratory insertion products out of this. So the first one, let's say we're going to place the phenyl ring in this position, then you're going to end up with something that looks like this. Palladium XLN. Or you can, of course, get the opposite one, where you have the phenyl ring on this side, and you get the palladium on the other position. So that basically, that selectivity for a simple alkyl substituent R is not very well defined, especially if this is an electron donating substituent. There's only one way where this is a little bit selective. So let's say first unselective for R equals an electron donating group. For electron withdrawing groups, you can rely on a little bit more selectivity. So if it's an electron withdrawing group here, and I just give you one simple example here. If you have an alpha beta unsaturated ester, OMe, for example, and you do this Heck reaction with this end here, the selectivity for the chemistry is going to be that the palladium ends up always in this position, and the alkyl group ends up in this position. So let's put the alkyl and palladium as part of this insertion. So if we react this with again our reagent here, palladium XLN, then we can make sure that the only product that we're going to get out of this migratory insertion selectively is going to be the one that has the palladium in this position, XLN, and then we still have our ester here. And after the reductive elimination, so you can draw the hydrogen here that you eliminate, you selectively get the conjugated product out of that. OMe, where basically you attach at the terminal end of the double bond, your substituent R. Now, this is selective for electron withdrawing groups. So if you have something like an ester, a nitrile, a carbonyl, an aldehyde, or something like that attached to this double bond, you can get this type of selectivity. If you have an electron donating group, you can expect to see a mixture of these two products. All right, this is basically the end to transition metal catalyzed reactions, and I want to end today's lecture at this point. Next time we are going to go into the chapter of pericyclic reactions. This is a completely new class of chemistry. It's one of these three main groups of reactions that I mentioned sometime during the lecture. Where we had essentially the reaction of a nucleophile and an electrophile as the polar reactions. Those were covering about 90% of the chemistry that we're doing usually. Then we have the pericyclic reactions. These are the ones that we're going to cover in the next couple of classes. This is the second class of reaction, and the third class is radicals. These are pretty rare. But we're going to cover them right at the end in the last two lectures in this series. All right, so I'll see you for next lecture on Tuesday at the same time again. You should all have the link for that. I will post the recording of this lecture right after I have rendered it. And I'll have office hours tomorrow at the regular time. The link is posted also on bCourses. Okay, so I hope I see you soon. Stay safe and stay healthy. Bye.
Thank you.